Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to just take a second, close your eyes maybe, and think about our moon, Luna, how absolutely vital it is. It's so big, so close, it feels fundamental, you know? We kind of take it for granted. We see the tides, sure, we see the moonlight. But do we really stop to think that if Earth hadn't captured that giant companion way back when, life like us, complex, long-lived life, it might never have even gotten started. Seriously, we could have been just this unstable, spinning rock wobbling all over the place with a crazy axial tilt. No stable climate. No chance, maybe. And that thought brings us right into this huge paradox in our search for life out there. We found thousands of exoplanets. Thousands. The galaxy seems packed with them. But exomoons, where are they? Logically, they have to be out there, right? We have zero confirmed ones. None. Just maybe a couple of interesting candidates that we're still squinting at. Finding them is tough, really tough. So astronomers have been focusing on where moons might matter most for habitability. And for a long time, that meant looking at planets around M-dwarfs. You know, the little red dwarf stars. They make up most of the stars in the galaxy. But it turns out the physics in those systems, it might be incredibly harsh, really destructive. So today we're diving into some fascinating new research. It's led by Sean Patel, and the paper's title really says it all. Tidally Torn, Why the Most Common Stars May Lack Large, Habitable Zone Moons. We're going to unpack the, well, terrifying orbital mechanics of these red dwarf systems and find out why the very conditions that might seem good for life could actually be destroying the moons life might need to hang on long term. Okay, so let's get into this. Is it possible that the most common places for planets in the galaxy are just moonless, or at least lack the big moons? What does that mean for finding another Earth?
It's a really pivotal question right now in astrobiology, absolutely. Because we use the Earth-Moon system as our benchmark, our sort of N-of-1 example for a habitable world, and when you compare our moon, Luna, to basically any other moon in our own solar system, the difference is just striking. Relative to Earth's size, our moon is enormous. That mass ratio planet to moon, it's way off the charts compared to Jupiter's moons or Saturn's. And that sheer size, that's where its incredible stabilizing power comes from.
Right, it's not just a pretty nightlight, it's doing heavy lifting, gravitationally speaking.
Exactly. The scientific consensus really is that without Luna, Earth's history, life's history, would look fundamentally different. If life even got going in the first place, which is a big if, we can kind of break down its key jobs for habitability into two main things. And we need to grasp both to really see what might be missing around those M-dwarfs.
Okay, let's start with the big one, the one that gives us stable climates over long, long periods. Axial tilt stability.
Yes. First up is axial stability. Earth tilts on its axis about 23.5 degrees right now. That gives us our regular seasons, predictable climate zones. Our moon acts like this giant gravitational gyroscope, basically. It keeps that tilt, the planet's obliquity, from swinging wildly over millions, even billions of years. Without that big moon acting as an anchor, models suggest Earth's tilt could wobble chaotically, maybe from, 0 degrees, so no seasons at all the way up to 85 degrees, where the poles are practically pointing straight at the sun.
Whoa. Okay, 85 degrees. What happens to a planet if its axis is swinging around like that? What are the consequences?
Cataclysmic is probably the right word. The climate shifts would be extreme. If the tilt gets too low, close to zero, the poles stay freezing cold, ice caps grow huge, maybe you trigger a runaway snowball Earth scenario. But if it swings the other way, it gets really extreme. You could get these incredibly rapid, violent climate swings, cycles of oceans potentially boiling near the equator, and then global deep freezes.
Yeah, trying to evolve anything more complex than maybe some hardy microbes in that kind of environment.
Yeah.
It sounds impossible.
It's hard to imagine. The moon essentially gifts us billions of years of relative climate stability. That consistent seasonality is probably crucial for complex life to emerge, diversify, and thrive. You just have to look at Mars. It only has these tiny little moons, Phobos and Deimos. They do basically nothing for stability. And Mars's axial tilt, it's known to have shifted dramatically over geological time.
Okay, so that's the climate regulation. Billions of years of stability. What's the second critical function? The one we see every day?
That's the more immediate biological driver, tidal action. The moon pulls on Earth's oceans, creating the tides. And this has really profound biological effects, especially thinking about early life and the transition from water to land, or its complexity in general. Those zones that get repeatedly covered and uncovered by water, the intertidal zones, they're incredible mixing bowls for nutrients. They constantly expose life forms to both water and air, driving really important adaptations early on.
I remember reading about that. Some theories suggest tidal pools, or these areas cycled by tides, were maybe key for concentrating the building blocks of life, the organic molecules needed to kick things off. So it's not just biodiversity later on, it could be about the origin itself.
Absolutely. There's a strong case to be made there. The tides dump enormous amounts of mechanical energy into the oceans and coastal areas. They stir things up. So whether life got its start near deep-sea hydrothermal vents or in shallow, sunlit pools, that constant mixing and movement driven by the moon is likely a critical factor. Which is why, when astronomers are looking out at other star systems, just finding a rocky planet in the habitable zone, well, it might not be enough. We really need to find systems that also have these big, stabilizing, potentially life-stirring moons.
And this isn't just a fringe idea, right? The search for exomoons is becoming pretty mainstream in the astronomy community. They see the need.
Oh, definitely. It's moved from theoretical wish lists right into actual observing plans for our best telescopes. I mean, prime observing time on the James Webb Space Telescope, JWST, has been specifically allocated to hunt for an exomoon.
Really? Which system are they looking at?
They're targeting a planet called TOI 700d. It's a rocky world, looks like it's smack in the middle of its star's habitable zone. And there are some, let's say, intriguing hints, nothing confirmed yet, but hints that it might host a large Luna-like moon.
Wow. So if JWST actually confirmed a big moon there, that would be huge. Game-changing.
We'd be revolutionary overnight. Suddenly, the idea of habitable worlds needing moons wouldn't just be based on our one example. We'd have another data point. But, and This is the big but from the Patel research we're talking about, the study suggests that these very systems we're most interested in, the M-dwarf systems like TOI 700s, might be fundamentally unable to keep a large moon like that for very long.
Okay, let's dive into that tension. Why M-dwarfs? Why are they both the most common places to look statistically and maybe the worst places for moons to survive physically? So just to set the scene again, M-dwarfs, red dwarfs. Small stars, cool, not very bright, but, and this is key, they make up something like 3/4 of all stars in the Milky Way. They're just everywhere. And we know from Kepler and TESS and other surveys that they often have rocky planets orbiting them, including planets in their habitable zones. So purely by numbers, M-dwarfs look like prime real estate.
Statistically, yes, absolutely. If you're playing the numbers game, M-dwarfs are where you place your bets. But the physics gets tricky. The biggest issue comes directly from them being so dim. Remember the habitable zone, the Goldilocks zone? Its distance is said by how much heat the star puts out. Because M-dwarfs are so faint, their habitable zones are incredibly close to the star. Way, way closer than Earth's orbit around our sun.
Okay, put that in perspective. How close are we talking?
Well, if you think about Earth being at 1 astronomical unit, 93 million miles from our sun, the habitable zone around a typical M-dwarf might be more like inside Mercury's orbit, maybe only a few million miles out from the star in some cases.
Wow, okay. That is close. And being that close has major consequences for a planet, and especially for its moon, right? Tidal sources must be immense.
Exactly. You get two huge tidal consequences.
The first one we hear about a lot with M-dwarf planets is tidal locking, where the planet always shows the same face to the star.
Correct. That close proximity makes it almost inevitable that the planet becomes tidally locked, just like our moon is locked to Earth. So you get one side perpetually baked by the star and the other side locked in permanent freezing night. Life might maybe find a niche in the terminator zone, that twilight ring around the edge, but that's a whole other challenge for habitability.
Okay, so tidal locking of the planet is one consequence. What's the second, the one that's critical for this research about moons?
The second consequence is the raw power of the stellar tides acting on the moon. Because the habitable zone planet is orbiting so incredibly close to the M-dwarf, the star's own gravity exerts this immense disruptive pull on any moon orbiting that planet. The star is basically in a constant, fierce gravitational competition with the planet, trying to steal its moon.
It really does sound like a cosmic tug-of-war. The planet's trying to hold onto its moon, but this huge star nearby keeps yanking on the rope.
That's a great way to picture it. And since we obviously can't sit and watch this gravitational battle play out over billions of years in real time, we have to simulate it.
Right, which brings up the question, How do you even model that? 3 massive objects, star, planet, moon, all pulling on each other, plus tides. It sounds computationally intense.
Oh, it is. Immensely so. Simple two-body gravity, like just a planet and a star or a planet and a moon, that's relatively straightforward. We have nice equations for that. But add that third body, the star pulling on the moon pulling on the star, everything interacting. It blows up into the classic 3-body problem. There's generally no neat, simple mathematical solution you can just write down.
So, no easy formula. How do they figure out if the moon stays or goes, and for how long?
The only practical way is through what are called n-body simulations. It's a numerical technique. Basically, you tell a computer the initial positions and velocities of the star, planet, and moon. Then the simulation calculates the gravitational force every object exerts on every other object over a tiny little time step, maybe just minutes of simulated time. It figures out how those forces change their paths, moves them to their new positions, and then it repeats again and again for millions or even billions of simulated years.
So they're essentially playing out a high-speed, high-precision video game of orbital mechanics, step by tiny step, over cosmic timescales.
That's a pretty good analogy, yeah. And for this particular study by Patel and his team, they couldn't just model the simple point mass gravity. They had to include the really complex effects of tidal forces. The star raises tides on the planet and the moon. The planet raises tides on the moon. These tides act like friction. They dissipate energy. They cause orbits to change. It all has to go into the simulation.
And what were the key things they changed in these simulations to see what mattered most?
They varied 2 main factors. The mass of the host planet. They looked at planets around 1 Earth mass, up to maybe 2 Earth masses, like a super-Earth. And crucially, they varied the planet's orbital distance, its semi-major axis, within the habitable zone.
That distance seems like it would be critical, because the further the planet is from the star, the less the star interferes, right? It defines the planet's gravitational turf.
Precisely. And that turf has a technical name that's central to this whole problem. The Hill sphere.
Okay, the Hill sphere. Explain that. What is it visually?
Imagine the planet is surrounded by an invisible bubble. Inside that bubble, the planet's own gravity is the dominant force. It's strong enough to hold on to an orbiting moon, even with the star pulling from farther away. That bubble is the Hill sphere. If the moon orbits nice and deep inside the Hill sphere, it's relatively safe. But if its orbit takes it too close to the edge of that bubble, or if the bubble itself shrinks, the star's gravity can become dominant, and it can pull the moon away.
Okay, so how does the Hill sphere behave in these tight M-dwarf systems compared to, say, our solar system?
Well, here, Earth is quite far from the sun, so our Hill sphere is pretty large, about 1.5 million kilometers across. Plenty of room for the moon, which orbits well inside that. But around an M-dwarf, the habitable zone planet is so close to the star. That powerful stellar gravity constantly squeezes the planet's Hill sphere, shrinking its zone of influence. The closer the planet orbits the star, the smaller its Hill sphere becomes. And the smaller the Hill sphere, the easier it is for any slight nudge or orbital evolution to push the moon outside that boundary, where the star can just snatch it.
So the setup itself is precarious. The planet might be at the right temperature for liquid water, but it's in absolutely the worst gravitational neighborhood for keeping a large moon safe. The deck is stacked against the moon from the start.
That's the fundamental challenge the simulations were designed to quantify. And the results? Well, they paint a pretty bleak picture for the idea of Earth-like worlds, with Luna-like moons being common around most red dwarfs. The headline finding, the general rule that emerged, is that rocky planets like Earth orbiting in the habitable zones of M-dwarf stars are highly likely to lose any large Luna-sized moons they might form, and they lose them fast, typically within the first billion years of the system's life.
A billion years sounds like a long time, but in planetary evolution terms, maybe not.
Compared to the 4.5 billion years Earth has had its moon, no, a billion years is short. But it gets much, much worse when you drill down into the specific types of M-dwarf.
Right, we can't just say M-dwarfs. They range from hotter, brighter ones to much cooler, dimmer ones. And that classification, M0 down to M9, must be critical here because it dictates how close that habitable zone is.
Absolutely critical. The classification basically tells you the star's temperature and brightness. M0 stars are the hottest and brightest M-dwarfs, relatively speaking. M9s are at the other end, tiny, ultra-cool, incredibly dim. Since the habitable zone location depends entirely on the star's heat output, this classification directly tells you how close an 8Z planet has to orbit. An M9's habitable zone is practically skimming the star's surface compared to an M0.
And closer means stronger stellar tides, more Hill sphere squeezing, more danger for the moon.
Precisely. So the researchers ran detailed simulations, focusing initially on systems around M4 dwarfs. These are kind of typical middle-of-the-road red dwarfs. They simulated these star-planet-moon setups for 200 million years to see what happened.
Okay, M4 systems. What was the verdict? How long did those Luna-like moons typically last? This feels like the moment of truth.
The results were, frankly, shocking. For these typical M4 dwarf systems, the simulation showed the average lifetime for a large Luna-like moon was less than 10 million years.
Wait, 10 million, not billion, million.
10 million years. 10 mir. It's an incredibly short timescale. Cosmically speaking, it's basically instantaneous. The moon forms maybe, and then poof, it's gone.
Okay, wow. I need to process that. 10 million years. Let's put that against Earth's history again. Life's history. What does 10 million years get you?
Almost nothing in terms of complex evolution. Earth is 4.5 billion years old. It took hundreds of millions of years just for the planet to cool down, for oceans to form, for the atmosphere to stabilize somewhat. Simple, single-celled life appeared relatively early, maybe within the first billion years, but complex life, multicellular organisms, animals, that took billions of years. The entire Cambrian explosion, the big diversification of animal life, happened around 540 million years ago. Dinosaurs existed for 165 million years, 10 million years. It's just a blip.
So, any benefits that moon might provide, the stable tilt, the ocean tides stirring things up, they'd vanish before life had any real chance to take advantage of them for the long haul. The stability needed for billions of years is only there for millions.
That's the devastating implication. The researchers explicitly state that 10 million years is very short compared to the astrobiological, geological, or astrophysical timescales. It means the moon is effectively useless for fostering the kind of long-term, stable conditions complex life seems to require.
And if that's the case for M4 stars, what about the even cooler, dimmer ones?
Yeah.
The M5s, M6s, all the way to M9s, where the habitable zone is even closer.
The prognosis gets even worse. Patel and the team extrapolate from their findings. They expect that habitable zone planets around those later type M-dwarfs, M5 through M9, will lose their large moons even faster than 10 million years. The stellar tides are just too overwhelming that close in. They rip the moon away almost immediately.
So for the vast majority of red dwarfs, the most common stars, if a planet forms with a big moon in the habitable zone, that moon is doomed. Its lifespan is negligible on cosmic timescales. The system is actively hostile to it.
That really seems to be the takeaway for M4s and later. And it's important to connect this finding the tidal tearing with other research that looked at a different problem, tidal heating.
Ah, right. So even if the moon somehow survived being ripped away, it might cook itself from the inside out.
Potentially, yes. Other studies suggested that even if a large moon managed to hang on for a while in that intense gravitational environment, the constant flexing and stretching from both the stars and the planet's gravity could generate enormous amounts of internal heat through friction. If it's an icy moon, maybe that creates a subsurface ocean, which sounds good, like Europa, but the heating could be so extreme it makes the ocean too hot or drives runaway volcanism, rendering the moon itself uninhabitable.
So it's a double whammy for big moons around most M-dwarfs.
Yeah.
They either get tidally torn away very quickly or they get tidally heated into oblivion, a real lose-lose situation.
That phrase, general fragility of exomoons in M-dwarf systems, really captures it well. For M4 through M9, the outlook seems incredibly poor if you need a large, stabilizing moon for planetary habitability.
It's hard not to feel a bit deflated by that.
Yeah.
Billions upon billions of star systems potentially hostile to the one feature that made Earth so stable. But science always has nuances, right? Were there any scenarios in the simulations where moons lasted longer? Any exceptions to this grim rule?
Yes, thankfully there were. The simulations didn't just paint a picture of destruction. They also pinpointed the specific, somewhat rare configurations where large moons could survive for significantly longer periods. And the key factor, again, was the star type.
Okay, so where did they find more hope? Which M-dwarfs offer a better chance?
The hope lies almost entirely with the earliest, hottest, and brightest M-dwarfs. The M0 stars.
M0s. What makes them different enough to potentially save a moon?
It all comes down to distance again. Being the brightest type of M-dwarf, an M0 star's habitable zone is pushed significantly further out compared to an M4 or an M9. It's still closer than Earth's orbit, but it's far enough to provide a crucial buffer. That extra distance dramatically weakens the star's tidal pull on the moon. It gives the planet's own gravity, its Hill sphere, a much better chance to hold on.
Okay, so moving the habitable zone outwards is key. How much longer could a moon last around an M0 in the simulations?
Significantly longer. The simulation showed that for a standard Earth-mass planet orbiting in the habitable zone of an M0 dwarf, a large Luna-like moon could survive for up to 1 billion years.
1 deer.
1 billion years. Okay, that's 100 times better than the 10 million years for the M4 scenario. That's starting to sound more useful, maybe.
It's definitely a huge improvement. As the researchers put it, the increased distance weakens the stellar tide and leaves a large part of the tidal action to the moon's tide that spins the host planet. Basically, the star becomes less of a bully, allowing the planet-moon dance to continue for much longer before the inevitable disruption. Did they try to find the absolute best-case scenario, like tweaking the planet size too?
They did. They pushed the parameters to find the maximum possible survival time. They simulated a more massive planet, a super-Earth of about 2 Earth masses, also orbiting in the habitable zone of an M0 dwarf. In that specific optimized scenario, biggest plausible planet mass orbiting the safest type of M-dwarf, M0, the moon could last for a calculated maximum of 1.35 billion years.
1.35 billion years. Okay, that's the absolute ceiling for moon stability in any M-dwarf habitable zone, according to these models. We need to anchor that number again. Put 1.35 billion years into Earth's timeline. Where does that land us? Is it long enough?
Well, it's still problematic, even at the maximum. Earth has had Luna stabilizing it for 4.5 billion years. If our moon had vanished 1.35 billion years after Earth formed, that would put its disappearance somewhere deep in the Proterozoic eon. We're talking about a time when oxygen was only just starting to really accumulate in the atmosphere during or after the Great Oxidation Event. It's long before complex animals appeared. It's certainly way before the Cambrian explosion around 540 million years ago, which marked that huge burst of diverse multicellular life.
So even in the absolute best, most favorable M-dwarf scenario, imaginable hottest M-dwarf, biggest planet, perfect orbit, the stabilizing moon is likely gone before complex life really gets going and needs that long-term stability the most. The clock runs out too soon?
The stability it offers is significant, but ultimately transient. It provides a decent runway, maybe long enough for simple life to get established, but it sets a firm expiration date well before the timescale over which complex Earth life evolved and relied on that stability. It really forces us to question, does planetary habitability require billions of years of stability from a large moon? Or can life adapt? These simulations strongly suggest that if you do need that long-term lunar anchor, M-dwarfs, even the best M0s, probably aren't the place to find it.
That's a profound adjustment to how we think about the search for life. M-dwarfs, abundant, yes, but maybe gravitationally unsuitable for Earth-style habitability.
That seems to be the core message regarding large moons. The study was focused on Luna-sized moons because those are the ones massive enough to significantly stabilize a planet's tilt and drive strong tides. But the researchers did acknowledge something important. What about small moons?
Ah, right. Moons like Mars's Phobos and Deimos, or maybe asteroid-sized moons like Ceres, could they survive?
Exactly. The simulations and the physics suggest that much smaller moons could potentially survive for billions of years, even around the cooler M-dwarfs. Their small mass means the star's tidal forces just don't have the same leverage to disrupt their orbits. They're gravitationally less significant. The star barely notices them. So it's possible these M-dwarf planets could be orbited by swarms of small, stable moons for eons.
But can we even see those? Are they detectable?
And that's the huge caveat. No, moons that small are currently completely beyond our detection capabilities. They don't create a strong enough gravitational wobble, TTV, or block enough light, transit depth variation, for us to spot them with current methods.
So the big stabilizing moons are likely gone fast, especially around most M-dwarfs. Smaller moons might survive, but we can't see them yet. It really does push the focus for finding Earth-like stability towards other types of stars, doesn't it?
It strongly suggests that if long-term stability from a large moon is a requirement, we probably need to focus more on stars like our own Sun G-type stars, or maybe even slightly hotter F-type stars. Around those stars, the habitable zones are much farther out. There's just more breathing room. The star's tidal influence at that distance is far weaker, allowing a planet to comfortably hold on to a large moon within its hill sphere for billions and billions of years. Plenty of time for complex life to potentially evolve under stable conditions.
So this study isn't saying moons are rare everywhere. It's saying large moons are likely rare and short-lived, specifically in the habitable zones of the most common stars, the M-dwarfs. The system architecture itself is the problem there.
Precisely. It highlights that the stability of the entire star-planet-moon system might be the critical bottleneck, maybe even more so than just having a planet in the right temperature zone. You need both proximity for warmth and distance for gravitational peace. And for M-dwarfs, those two needs seem fundamentally incompatible for large moons.
Okay, so the theory and the simulations paint a compelling, if somewhat challenging, picture. But theory needs observation. Where do we stand on actually finding any exomoons, large or small?
Well, that's the ongoing challenge. As we said at the start, despite thousands of exoplanets, we still have 0 definitively confirmed exomoons. 0.
And detecting them is just incredibly hard, technically. You mentioned the methods transit timing variations, TTVs, and transit duration variations, TDVs. Can you explain those a bit more? How subtle are the signals we're looking for?
They are unbelievably subtle. Imagine watching a planet pass in front of its star that's a transit. If that planet has a moon, the moon's gravity constantly tugs on the planet, pulling it slightly ahead or behind in its orbit. So instead of the transits happening with perfect clockwork regularity, they might occur a few seconds or minutes early one time, then a bit late the next. That tiny wobble in the timing is the TTV signal. Similarly, the moon's gravity can slightly alter the planet's path during the transit itself, making the transit last a tiny bit longer or shorter than expected. That's the TTV signal.
Seconds or minutes difference over journeys that take days or weeks, viewed from light years away. Yeah, I can see why that's tough. It must be incredibly easy to mistake noise or interference from other planets for a moon signal.
Exactly. Disentangling a faint moon signal from instrumental noise, stellar activity, or the gravitational nudges of other unseen planets in the system is a massive data analysis challenge. We have candidates, like the one around Kepler 1625b or Kepler 1708b, but confirming them beyond doubt has proven extremely difficult.
But technology doesn't stand still. Are there new telescopes or instruments coming online soon that might finally give us the breakthrough we need? Can we test these simulation results from Battel's team directly?
That's the big hope for the next decade or two. There are some potentially game-changing facilities on the horizon, both in space and on the ground. In space, the big one being discussed is the Habitable Worlds Observatory, HWO. This is envisioned as NASA's next flagship astrophysics mission after Webb and Roman. If it gets built, its primary goal is to directly image Earth-like exoplanets around sun-like stars. It would likely feature a large mirror, maybe 6 to 8 meters across, and crucially advanced technology like a coronagraph or a separate star-shaped spacecraft. These are designed to block out the overwhelming glare of the host star.
Okay, blocking the starlight. Why is that so critical for finding moons specifically?
Because moons don't produce their own light. They only reflect their star's light. And that reflected light is incredibly faint, billions of times dimmer than the star itself. It gets completely lost in the star's glare with current telescopes. By suppressing the starlight very effectively, HWO could potentially allow us to not just detect the indirect gravitational wobble, TTV, TDV, but maybe even directly see the faint light reflected off a large exomoon orbiting an exoplanet, or at least characterize the planet-moon system much better.
Direct imaging of an exomoon. That would be incredible. What about ground-based telescopes? Are the new giant telescopes going to help?
Absolutely. On the ground, we're looking forward to the next generation of extremely large telescopes, like the Giant Magellan Telescope, GMT, in Chile. This beast will have a primary mirror, effectively 24.5 meters across huge light-collecting power. While ground-based telescopes have to deal with Earth's atmosphere blowing the view, the GMT will use sophisticated adaptive optic systems to correct for that distortion in real time.
So, sharper images from the ground.
Incredibly sharp. The combination of its sheer size and advanced optics should allow GMT, expected to start observations in the 2030s, to directly image some nearby exoplanets, especially larger ones orbiting a bit further from their stars. And if you can directly image the planet, you can track its motion very precisely. If it's wobbling due to an unseen moon, GMT might be able to detect that wobble with much higher fidelity than current instruments, potentially confirming moon candidates or even discovering new ones, especially around closer stars where the angular separation is larger.
So between HWO in space potentially giving us direct light and GMT on the ground giving us ultra-precise motion tracking, the next 10-15 years could be really exciting for exomoon science. We might finally get some observational data to compare against these theoretical predictions about M-dwarfs.
That's exactly the goal. We need to bridge the gap between these sophisticated simulations and actual observations. We need to see if large moons really are rare around M0 stars and essentially non-existent around M4, M9s, as Battel's work suggests. Or maybe nature has found a way we haven't anticipated. And finding them is so important for two big reasons related to the search for life. First, as we've hammered home, a large moon might make its planet habitable through stability and tides, like Luna does for Earth. But second, there's the flip side. The moon itself could be a habitable world. We can't ignore that possibility.
Like the icy moons in our own outer solar system, Europa, Enceladus.
Exactly. Even if an exomoon is in a system where it experiences significant tidal heating, maybe too much for the planet, or even too much for surface life on the moon, that internal heat could potentially maintain a liquid water ocean beneath an icy shell. We're actively exploring whether such subsurface oceans on Europa or Enceladus could harbor life right here. The same potential exists for exomoons, possibly even some of those tidally heated moons around M-dwarfs, if they manage to survive long enough in some configuration.
So finding exomoons opens up two potential avenues for life beyond Earth. Wow. Okay, let's try to tie this all together if we step back and look at the big picture from this research.
I think the core message connecting everything is that planetary habitability isn't just about being in the right temperature zone. The stability of the entire system's architecture, especially concerning large moons, seems to be a critical prerequisite, at least for Earth-like life. And this study by Patel and his colleagues really challenges the long-held assumption that M-dwarfs are the prime targets just because they're numerous and have HZ planets. If that potential life needs the long-term stabilizing hug of a massive moon, the intense gravitational environment close to these common stars appears to be fundamentally hostile. It tears those moons away.
It suggests that finding that sweet spot, close enough for warmth, but far enough for gravitational stability for a moon, might be much rarer than we thought. That specific architecture might be the real bottleneck.
It could very well be. Maybe having a large, stable, long-lived moon is one of the rarest variables in the Drake equation, if you will. We need the observations to find out.
This has been absolutely fascinating, really digging into the physics of these tiny, turbulent star systems. Okay, let's quickly recap the main takeaways you've gotten from our discussion on this tidally torn research. First, you understand now just how crucial a large moon like ours is for keeping Earth's tilt stable over billions of years, and for driving ocean tides that might be linked to life's origins and complexity. Second, you know that M-dwarfs, the most common stars, have habitable zones snuggled up incredibly close, and that closeness means the star's gravity wreaks havoc on any large moons, creating intense tidal forces. Third, the simulations show that for typical M-dwarfs, like M4s, these crucial large moons likely last less than 10 million years. That's just far too short for complex Earth-like life to evolve needing that stability. Fourth, there are rare exceptions. Around the hottest M-dwarfs, M0s, where the HD is further out, a moon might last up to maybe 1.35 billion years in the best-case scenario. But even that's likely not long enough compared to Earth's 4.5 billion years of lunar partnership. So, fifth, you now see why the search for planets with long-term moon-stabilized habitability might need to shift focus slightly away from the most common stars and more towards stars like our Sun, where there's more gravitational room for moons to survive long-term. But here's a final thought I want to leave you with, something sparked by our conversation about those other moons. The study focused on the big Luna-like moons needed to stabilize a planet. We also mentioned that tiny moons, maybe Ceres size or Phobos size, could potentially survive for billions of years, even around M-dwarfs, although we can't detect them yet. Now, what if? What if those small, stable, currently invisible moons are habitable in their own right? Maybe they have subsurface oceans kept liquid by just enough tidal heating, not the runaway kind, but a gentle, long-term warmth, if that's possible. Are we perhaps looking for life in the wrong place entirely? Should we be thinking less about moons that help their planets, and more about tiny moons that manage to survive and thrive despite their chaotic planetary and stellar neighborhood? Just something to ponder next time you look up.